Exciting subject. Here's some homework. I know you guys love homework. You can pass that around. There you go. If anyone doesn't get the homework, there's some more up here. You can get one right here. So if anyone doesn't get one, there's a bunch of them passing around. So we'll give you the homework too. Now we're going to come up on the design section. The homework has to do with everything. All the answers are in the design section. So the design section is coming up. So let's go ahead and get going again. One of the things that we always deal with is changes. They can always be a problem. We try to accommodate them if we can, but changes can be you change a little thing, and it can have other implications that you're not aware of. It kind of sometimes it's a little bit of a domino effect. So just be mindful that we try to keep the changes to a minimum. It has an impact on manpower and scheduling, and it can. And it's if we have changes in scope, if it's a bigger change, then we have a big change, a big scope change. It's a big difference. So anyway, we try to control the changes. Make sure that we have to actually make a change, and if we can avoid it, we do. But sometimes we have to. So go ahead. Again, we're talking about we try to get things to other disciplines as they're required as quickly as possible in a timely manner. We want to get the base plate and anchor bolt design to structural, which gives them the loads, the overturning moments, and all that sort of information. Nozzle projections, piping doesn't know necessarily what the projection from the vessel is, so we have to give them that information. And elevations that, like I said before, elevations that impact the internals of the vessel. And sometimes the vessel nozzle have to be changed in order to accommodate the design of the internals. So go ahead. Okay, pressure vessel design. I passed out the homework. All the homework questions relate to this pressure vessel design area, so we can go ahead and get started on that. Okay. When we talk about the theory of pressure vessels, and it's a thin shell theory, there's two basic for a cylinder, and that's really what most vessels that we design are. They're usually a cylindrical shape with heads on each end. In the real world, the perfect vessel is a sphere. That's the thinnest vessel you can make. It would be the most economical, except a sphere doesn't always work for the processes we want. And because of that, the second best is to have a cylinder with heads on it. And the basic formula for stress is right here. Circumferential stress is PR over T. So that's pressure or radius times the pressure divided by the thickness. And that gives you the stress that's exerted in the circumferential, that's around the cylindrical portion of the vessel. That's also called the hoop stress or radial stress. It's all the same thing. It's just different terms for the same thing. So it's circumferential, radial, or hoop stress. It's all the same thing. For longitudinal stress, which is the stress along the longitudinal direction, in the longitudinal direction of the cylinder, it's PR over 2T. Or I think they have it R over R the other way around, but still it's the same formula. So it's RP over 2T. So as you can see, the circumferential stress is twice as great as the longitudinal stress. Now the question is, when we were looking at that really tall vessel, we noticed that as we went down we started from the top and worked our way down, it got thicker and thicker. Well, the reason it got thicker and thicker was because this longitudinal stress, due to bending, kept getting higher and higher. So the bending stress plus this longitudinal stress determines the thickness of the shell. So if you have additional bending, that's what pushes the thickness up. Is this stress plus longitudinal bending?
Isn't the bottom stress also dictated by the fact that if you have a very tall vessel, the fluids that you have
yes.
accommodate is also heavy?
Yeah.
Have a higher stress in the bottom?
That's correct. If you have liquids in the vessel, this value P gets increases by the static head of the liquid in the vessel. So if you add, whenever we talk about, that's a good point though, whenever we talk about pressure in a vessel, the design pressure in a vessel, when it's defined by the process group or shown on our drawing and per the ASME code, it's the pressure at the top of the vessel. So if you say it's 15 psi, that's the pressure at the top of the vessel. If there's liquid in the vessel, that has to be added to the pressure at the bottom. Okay, so the actual design pressure, if you have 10 feet of liquid head, you've got about a half a psi pressure from that. So that increases or actually about 5 psi, about 5 psi of additional pressure from 10 feet of liquid. So if you do that, you have to design that lower area for that higher pressure. So as the pressure increases, and that does increase the thickness. So you have really three things. You have especially for that particular vessel that we were talking about, you have the internal pressure increased by the static head, and you have bending, and then you have the longitudinal stress. So all those things add to it. So okay, going on. This is kind of the way this is an explanation of how they derive the basic formulas. And what's interesting here is they talk about what the force is, or how to derive the force on the head from internal pressure. So if you have internal pressure, how much force would you see on this head? You know, if you have a certain, like 15 psi, what does it all add up to? And it goes back to your 1 psi, your little 1 inch, your 1 square inch of pressure. That pressure is over the face of that whole surface, and that creates a total force. So whenever you're talking about pressure, you think about that 1 square inch. And for instance, we talked about the limit in pressure for the code of 3,000 psi. 3,000 psi, that's about 1.5 Volkswagens force on that 1 little square inch you have out there. 1.5 Volkswagens sitting on that at every little square inch throughout the whole vessel. So that gives you an idea to visualize what kind of pressures we're talking about, especially when you get into the higher pressures. So this is how they show you how you derive longitudinal and circumferential stresses, and then this is the force on a head. Okay, go ahead. This is really the code formula. Now, what you can see is the code formula is derived from the basic formula of PR over T, but we're solving for T now, so it's PR over stress. So the basic formula is PR divided by the stress equals the thickness. Now, what they've done is they've added E, which is a joint efficiency, and they've added an adjustment for thin shell theory. So it's kind of it's an adjustment to make the formula a little more accurate, and then also the E is a joint efficiency, which is defined as it really has to do with your weld efficiency, and it really defines on how much the weld is inspected and it gives you a certain amount of, I guess, confidence in the weld. So if you do, let's say you do 100% radiograph of your welds, now I have 100% confidence of the weld. So if I have 100% X-ray, then that E number can be 1. So we take full advantage of it. But let's say I don't want to do that. I don't want to spend that much money. I only want to, I don't want to inspect part of it. I only want to do a spot X-ray. Well, if I do that, now I don't have as much confidence that the weld is good. Even though we have weld qualification, but I still don't have as much confidence. So now we say the joint efficiency is 0.85. Okay, and that's per code. That's per UW12. So going on beyond that, let's say I don't want to do an X-ray at all. If I don't do an X-ray at all, this E number goes down to 0.7. And that's assuming we have a good weld design, which is called a type 1 weld. Okay, go ahead. Now this is a material chart, and it's got a few materials that we run into, and one of the most common materials that we see in pressure vessel design is SA 51670. And this chart here gives you the design, the alloy design UNS number, which is a separate organization that defines material types. But we have various grades of carbon steel here. We don't have anything that's exotic or anything, but some various grades of carbon steel. And if you look at line 30, that's SA 51670. Now, if you want to know any information about 51670, you go here to line 30, then you go down here to line 30. Now that tells you that the minimum tensile strength is 70, like we talked about before. This is at room temperature. The yield strength is 38 KSI, or 38,000 PSI. And then for section 1, it's good to 850 degrees. For section 3, it's good to 700 degrees. And for section 8, division 1, it's good to 1,000 degrees. So this is how you read this chart. And then you go down, you want to know what the allowable stresses are. You go back down here, and it gives you by temperature and by material, and you can read the chart. You can read the values from that. So go ahead. So again, here's the formula for, this is the code formula for longitudinal stress. And again, it's the same thing. You have the joint efficiency, and you have an adjustment for thin shell theory. And then this is the same formula for pressure. So if you have the thickness and you want to know what the maximum pressure is, this is the formula you use for that. And they had the same thing for the circumferential stress as well.
Do you have the corrosion allowance?
I'm sorry?
Do you have the corrosion allowance?
Yes, you do. That is something that you have to take care of. The corrosion allowance, these formulas assume that there is no corrosion allowance at the beginning, so they have to be adjusted for corrosion allowance. For instance, your radius would increase by the corrosion allowance. So let's say you have a 24-inch radius, then you have an 1/8 of an inch corrosion allowance, then in the formula you would put your radius of 24 and an 8 plus an 1/8, so it would be 24 and an 1/8 is your radius in the formula.
So that would be the radius, the internal radius, or
your internal radius. Yeah, because it is based on internal. Because if you look at the basic formula, the basic formula is the mean radius in reality. So it's the radius right through the middle of your material, your metal. Okay, so that's what this adjustment, this 0.4 and this 0.6 is to bring the formula into the ID of the vessel. So that's what the adjustment is for. So if you and then when you get resolution to your problem, now that you've used the corrosion allowance in your formula, then you have to add the corrosion allowance for your thickness, because you have a thickness based on what's the required thickness for internal pressure. Now, if you want to add the corrosion allowance, you have to add the corrosion allowance again. So, okay, go ahead. And then this just happens to be the formula for spherical shells, so we won't talk about that much. And then this is just kind of parts of a pressure vessel here. We have hemispherical head on this particular diagram, and then it just shows some various nozzles and connections, materials, conical reducer, and these are the kind of things you run into. They have a torus spherical head. Now the difference between what we use most is called a 2-to-1 semi-elliptical head or ellipsoidal head, and which means that the ratio of depth to width to diameter is 2-to-1. A torus spherical head is a sphere with knuckle radii, and it doesn't necessarily have to be the same as a 2-to-1 head. 2-to-1 head is a true ellipse, and this is not a true ellipse. It's a combination of a sphere and a knuckle radius. And sometimes these conical reducers have knuckle radii on them at the bottom and at the top. They're very expensive, though, but they're in some higher pressure applications, they are necessary. Okay, going on. This is a little bit what you were asking on how you do the formula here. You have you're checking for thickness here, so they have 150 psi. They have a diameter that's 120 inches, so they're dividing the diameter in half, and then they're adding the corrosion allowance. Now they divided it by an allowable stress. They have a joint efficiency of 1, and then again they have this adjustment factor for the ID, which is 0.6 times the pressure. So, and then they come up with this thickness of 0.757, and then as you can see, what's the thickness required? The thickness required is the 0.757 plus the corrosion allowance, which is 0.882. Okay, so that's exactly what you were asking. And the same thing holds true for longitudinal stresses. And the reason, even though you may think, oh, I don't have to calculate the longitudinal stress, the reason again is like we were talking before. When you have something that's very tall, especially, I mean, initially you want to look at the circumferential stress, because that's usually on a small vessel. That's what's going to govern. But when the vessel gets very big, you have to look at the longitudinal stresses as well and see what the combined stresses do to you, because they can, like was in the example that we showed before, the thickness became very thick because of the combined longitudinal and overturning and bending moments due to overturning.
The top of the vessel is thinner than the bottom of the vessel.
That's correct.
Do they average out a thickness for the tallest ones?
No.
For the longitudinal stress?
No, they don't average it out. It's really for each section. For instance, if you build a vessel, normally vessel sections are in either 8 or 10 feet length. So they make the cylinders in either 8 or 10 feet. So as you start off at the bottom and you have an 8-foot cylinder, you calculate what the thickness has to be for that section. Then you go back up. Now you calculate what the thickness is for that section. So you work your way up, and as you work your way up, it's going to get thinner and thinner and thinner. Eventually, you get down to your minimum thickness. So it's really not an average. It's just it's a calculated value at each elevation. Okay, go ahead. Okay, Amy, go ahead. All right, let's see here. We can go ahead and. This is just an example of a horizontal vessel, and one of the things that's important to note is that they show little wheels here. But what's important to know is a horizontal vessel, there's always an anchored or fixed end and a sliding end. Because as this thing heats up, it grows, and in very big vessels, it can grow quite a bit. It can grow, a few inches in length, and so this has to slide along the top of the foundation in order to accommodate the thermal stresses and the thermal expansion of the vessel. And it can grow. Also, it's going to grow in diameter as well a little bit. And then, of course, there's speaking of longitudinal stresses again. Whenever you support a vessel on saddles like this, you're going to have, this acts like a beam, so that what you have is you have bending stresses here, and you have a lot of localized stresses here at the support. So you have bending stresses due to this vessel wanting to sag in the middle due to the weight of the contents and the weight of the vessel itself, and then you have localized stresses that are here in the shell as a result of the saddle that holds it up in place. Go ahead. And again, I think this is a little calculation, a little example of some calculations. But one of the important things is one of the things that you brought up was liquid head. Right here, they've calculated. You have a pressure of 490 psi, and then they've got 8 feet of liquid on there. And the liquid is water, and it's at 62.4 pounds per cubic foot. And so they want to get what the pressure is, so they divide it by 144 cubic inches, square inches per square foot. And so that gives them about 3.5 psi. So they add that together, they get 193.5 psi. And so when you go back into the formula, and you're at that low level, that 8 feet ahead, then you have to add that value, and that's how you get a revised pressure and a revised thickness because of the liquid head. So you can go ahead. And that's just another example. So we could go ahead. The next little section here is gives you some formulas for heads and transitions. So if we go on to the next. Slide here. This is a 2-to-1 semi-elliptical head, or ellipsoid. I can't even speak. Ellipsoidal head. This is the formula for thickness and for pressure for that shape. And again, it's derived from the basic pressure formulas for stress on a shell. And this picture is just some people working on a head, so it just kind of shows you what this is a fairly large size, so you can see the people working here. So you can go ahead. And then this is just some more formulas. Torospherical head. Like I said, this is made up of you have a radius and a knuckle radius. So you have a dome radius and a knuckle radius. And then here's a hemispherical heads. Now hemispherical heads, you don't see them a lot because they're kind of expensive to build, but you do see them a lot when we have high pressures. And the reason is that a hemisphere is going to be about half as thick as a cylinder. And it goes back to the longitudinal versus the circumferential stress. So this is approximately the same thickness that would be required for the longitudinal stress on this head. So let's say you have you have a vessel that's the cylinder is 6 inches thick. This is going to be about 3 inches thick. And in that case, it becomes economical to spend the extra money because there's more welding involved and there's more shaping involved in order to get this kind of a head. So that's why you'll see this on reactors and that sort of equipment, because it's more economical to build this than it is to have a 2-to-1 elliptical head. Go ahead. And this is just an example of a cone, and it gives you some formulas for it. So we can go ahead with that. Now, this is a chart that tells you that the types of weld and the weld classifications. And let's see, I think I'm running a little bit slow, so I won't go through this in depth. But you have category A welds, and these are located right here. Category A and B welds are really your primary types of welds. They're your primary welds on the pressure boundary, and these are very critical in the design. And you usually want to. This is really where you want to have good. You have to have good quality here in all cases anyway. So you can go ahead. Again, this is essentially the same chart where we're talking about weld categories. But in addition to that, this goes back to a little bit about joint efficiency. And when you have certain combinations of types of shells, for instance, if this head doesn't have a seam, if it's small enough it doesn't have a seam, then you can have a higher joint efficiency here because it doesn't have a seam, so it doesn't have a weld. So this is kind of a layout of that information down here. So you can go ahead. This is an example of, again, we're talking about weld efficiency and weld types. This is a type 1 weld. This is your basic weld that you want to see at a pressure boundary. Now, there's other types of welds. There's welds that are fillet welds. There's double fillet welds, and those are all different types of different types of welds. But for the most part, this is the kind of weld that you want to see in a pressure vessel. Is a double butt weld that is a type 1 weld, and depending on when you have a type 1 weld, this is where the joint efficiency can be 1 if it's fully X-rayed, 0.85 if it's spot X-rayed, or 0.7 if it's visually inspected. And these rates actually change depending on the type of weld that you have. So, but that is outlined in the code. Okay, go ahead. Reinforcement. Whenever you punch a hole in a pressure boundary, you can't just walk away from it because you have areas, it's going to get highly stressed there because you open up a hole in it, and you can't just leave it the way it is. So you have to put a reinforcement. You have to put some kind of reinforcement. It might be a reinforcement pad or a reinforcing pad. It might be an increase in thickness on the nozzle neck in order to give you the type of stiffness that you need to reinforce the opening. But in all cases, you have to have reinforcement if the nozzle is over 2 inches. If it's less than 2 inches, then I guess they figure if it blows up, then you don't have to worry about it. No, I'm just joking. But anyway, you have to have reinforcement. You can go ahead, Amy. So this is how it's calculated. So you open up this area. This is the area that's removed here. So you have to, the same amount of area that you removed here, you have to add back out here some way. And this is the areas that you could add. You could add weld, your welding counts, your excess material here due to internal pressure. You can't take into account any material that you're using already for internal pressure, but you can use the area if you have something extra. If it's thicker than it has to be because of due to internal pressure, then you have the ability to use that thickness as part of your reinforcement. So this whole thing is a calculation. You add all this up, and all this stuff has to be greater than this. So that's what it really comes down to. So you just can't, like I said, you just can't cut a hole in there and leave it as that. You have to do something about it. Okay? And let's see, where does that leave us? That leaves us, I believe, with loads. Okay. Let's talk a little bit about UG22. UG22 is a section of the code, and I didn't print it out, but UG22 is a section of the code defines all the load requirements. So basically what it tells you is that any known loads, you have to design for them. And it doesn't tell you what they are, but it tells you, well, you know, if you know something, you got to design for it. So that means if you have a seismic load, you have a wind load, you better design for them. If you have local loads, you have things hanging off the thing, you better design for them. If you have some kind of cycling that happens as a result of the process, you have to design for it. And it doesn't necessarily tell you how to design for it, but it does tell you that you have to design for it. So you have to address it in some manner. So when it comes down to, it just gives you an outline of what you have to have. So that means internal and external pressure. We haven't talked about, we kind of skipped external